Hello, this is Lab 5, Motion of a Falling Slinky. The purpose of this lab is to analyze the motion of a falling slinky and understand the physical reasons behind it, and then create a model that reflects the experiment. The model of the slinky was created using GlowScript. Some prevalent physical principles include the spring force, gravity, tension, the momentum principle, and Newton's second law. The main result of the experiment is that the model does not reflect the experiment due to physical constraints. The spring force is calculated by multiplying the negative of the spring constant times the displacement of the spring from its equilibrium position times the unit vector. Gravity is calculated by multiplying the mass of the object times the acceleration due to gravity. There is no real equation for tension. We calculate it by using the other forces acting on the system when it's in equilibrium. The momentum principle and Newton's second law both say that the momentum is equal to the impulse. Even though they look different, they are the same thing. In the model and the experiment, the system was a spring, and the surroundings were the Earth and the universe. The top of the slinky has the initial position at the origin, and the bottom of the slinky has the initial position of negative 1.232 meters in the y direction. Both the top and the bottom start out at rest. The slinky was reduced to 2-point particles, the top and the bottom. Modeling the entire spring is too hard for the scope of this class, so this simplification was made to make everything easier. We are only interested in the motion of these particles anyways, and it's similar to analyzing the forces in an extended system at the point of application. The calculated spring force and gravity at each point was added together to calculate the net force acting on each particle. The motion of each particle was updated independently of each other. I used the momentum principle to update the velocity and position of each point particle. Here's a picture of the model. The green point is the top of the spring, and the red point is the bottom of the spring. For the experiment, a video of Veritasium's slinky drop was analyzed using Tracker. Both the top and the bottom of the spring were analyzed. As you can see, from the y position versus time graph, the top of the slinky begins to fall immediately, but the bottom of the slinky stays stationary in the air, but begins to fall when the top part catches up to it. In the model, both parts fall down, which does not fit into the results of the experiment. However, the bottom part has a lesser acceleration than the top part, which kind of fits into the result of the experiment, although the bottom part did not move at all. The main source of error in the model was that all physical models concerning springs in this class assume that the spring is massless, which is not the case in real life. This is important because we are considering the tension and gravity in the spring, and this depends on the mass of the spring. Also, the model was made using the spring force, which should stay constant in the experiment for the bottom part. The reason why the bottom doesn't move is because the spring force up and the gravity force down cancel out. However, in the model, the spring force for the bottom part is decreasing because L decreases, so it is affected by gravity the whole time. Not considering the mass of the spring in the model is a huge source of error, but it is outside the scope of this class. Modeling that using Python would require extensive knowledge of shape creation, and getting into the exact physics of the situation is complicated. Thank you and have a great day.